Okay. What do you guys want to hit up first?
I went on exam 2. My black
Okay.
house was done, and I wrote out some questions.
Do you happen to know what the exam, what do you mean exam 2? Do you mean 1070
20.
lesson?
Uh,
You mean looking on my webpage is the 1070 exam lesson?
yes, I found it near the bottom.
Okay, sounds good. Also, a good place to look at like exam 2, the ones that are called 1060 or 160 or 165, there's a long of the calculus ones. You're probably going to look at probably the second, third exams on, probably the third, if you want some other problems. So let's look at, I'll call that up here. So what do you want to look at on that exam? So this is, it's talking about the 1070 from last summer.
I was hoping we could just start with like 1A, just to go over those. I was a little rusty in those.
Okay, that's a good idea. Let's see. 1A is the limit as x goes to 1. Let's say x5 plus x3 equals 2. Actually, before I do the problem, x2. By the way, what's that limit? This is not 1A, it's variant. What's the answer to this? Yeah. Ah, where are we going? We're going to 1, right? So, actually, the top heavy, if we were going to infinity, this limit would actually be, infinity. Yeah, it would be infinity, because your top heavy, as you said. We're going to 1, so what do you get? What's it?
1/3.
That's exactly right. So here's the moral to this little side story. The first thing to always do with limits is just plug it in and see what happens, right? When I plug in here, I get 1 plus 1 plus 2, and here I get 1 plus 2 plus 3 plus 6, which is 4/12, which is 1/3, and there you go. Right, so don't, however, this wasn't the problem. Here's the problem. That's 1. Here's the real problem. Now it's not so easy. But again, a starting point should be a bonehead and plug in. Right? If you plug into the top, what do you get? And if you plug into the bottom, you get 0. By the way, if you've got 0 over 5, that's 0. If you got 5 over 0, this kind of function that would indicate that there's well, vertical asymptote, the one that doesn't exist, or it's infinity, or it's minus infinity. One of those 3. Here you get 0 over 0. Now, 0 over 0 is always a message from on high that says there's more work to be done. Right? Now, you could have done this actually in 1040 by factoring, right? Because what do we plug in? 1, and we got 0, 0. That means this has to have a factor of x minus 1, and this has a factor of x minus 1. So you can go through and divide, and something I don't probably know this today, but please don't, right? It's going to take a moment. This is why L'Hopital's rule is so much easier for this problem. So 0 over 0, let's give L'Hopital's rule a shot, see if it works out for us. Derivative at the top. Derivative of the bottom. Now plug in and see if you get something concrete, and yes, indeed, you do. I get 8 hence. What would have happened if I had gotten 0 over 0 again? I would use L'Hopital's rule again, right? Don't confuse L'Hopital's rule with the quotient rule. Sometimes people did that. Don't confuse it in either direction. This is something different than the quotient rule. Fine. So, 18. Okay, what else we got?
I just went down the line, some of these I tried to work through, so, I think 1B and then 1D after that. I think
Could you do C?
I did,
No, we'll go through that in a moment. Let's see. Limit, okay, so B, I mean, I can go through all these. Limit if X goes to 0. Sine of 2x squared, sine squared 3x. Sine squared 3. So the limit, X goes to 0, of the e to the tangent of sine 2x squared over sine squared 3x. Okay, the first thing that always is just see what you can get away with, plug them in. And if you plug in, it's all, the x's are all buried way up here. If I plug in x equals 0 to this, I get sine of 0, which is over 0, 0. So I can't even plug that in. Now, the exponential and the tangent are continuous functions, or at least continuous on their domains. Look, the tangent has a bunch of discontinuities, but it's continuous everywhere it's defined. In a certain sense, that tangent x, or that e and that tangent, they're kind of red herrings, right? In a way. Let's do a little aside here. This is a much more digestible chunk, right? Let's see just what happens. Okay, so let's be about and plug in 0 to 0, just like we got. So this sounds like a job for what it tells me. Gotta try to get this right. So derivative top, cosine of blob. Am I done? Comes the derivative of blob, which is 4x. Meanwhile, on the bottom, what do I have? In fact, another way to write this, it makes you comfortable. That's what that notation sine squared means, sine of 3x squared. What's the derivative of this? The first thing I come to is blob squared, right? Great. So this is 2 blob in the first power. Now I gotta multiply that by the derivative of what I find inside there. What's the derivative of sine 3x? Cosine 3x, and am I done? Good, very good, excellent. Yep. This is, let me do one constant stat. I agree with that, that's just a little rearrangement. I took the X here, and then I took the four cosine. X right here. I took the sine three X by its lumps, and then just like the six. Do I agree? Same thing, and I do this for dramatic effect. I've done a little calculus once, now what do? You plug in, and what do you get when you plug in? You get zero for zero, everybody agree with that? Because, and here I highlighted, right, because this gives you zero, but this actually gives you four, doesn't it? This is not an offender in service. This gives you zero, but this gives you six, right? So really, let's do this. Aside two. Because nobody wants to take the derivative of this, do you? Any volunteers for this? Because this is a product rule with a chain rule, and this is probably even worse, right? Nobody wants to take the derivative. So let's do this. See what I've done here? I pulled the offenders out. Those are those are the things that are creating the zero over zero. Everything that makes zeros, I take it out. This is zero over zero, so let's apply what we call rule of this. What's the derivative of x? Derivative of sine 3x. Is that it? Very good. And this limit is easy to figure out, because all you gotta do is plug in this 1/3. So using this fact here, this becomes, this limit is 1/3, and this gives me times 4/6. So that's gonna be 2/3 times 1/3, which is 2 months. Back to the original problem. What's the next? Get it? Oh, so what did it use? What's it got? What do you hope it is? There's a theorem from 1040. When you talk about continuous functions, it says if you have continuous functions to evaluate a limit, like all you have to do is do the limit what's inside. There you go. The real heavy lifting of this problem is just figuring out what goes on inside this tangent. We got that answer. It was 2 numbers, and the answer is equal. Whatever. Actually, that is not a coincidence. And I knew what this limit was before I did L'Hopital's rule, because I know what the power series for sine x is, and so will you by the end of 1080. So that'll be another way that you'll learn to do this. Yes, that's a good observation. That is not a coincidence that it was 2 over the square of 3, but it might be hard at this point to pick up the. Yeah, the only thing they did is, so if I really pick this apart, this is e to the limit x goes to 0, a tangent of sine of 2x squared over sine squared 3x, which is again e to the tangent limit as x goes to 0 sine 2x squared over sine squared 3x. And this works as long as exponentials continuous everywhere, and as long as this is point of continuity, tangent, it is. There's no time. It's not a rational. It's not a form change by number two. Okay. Other questions? Oh, yeah, we'll get that. Actually, you wanted to see what, do you want me to finish these limits up?
I need to work on, I have a better grasp of it.
Okay.
I would like you to take a look at one of them, because I got kind of stuck on like a continuous loop, and I think it was one D.
Okay, yeah, okay, that's good. Yeah, after this, we'll look up the quiz. I think it's good. Quiz here. So, what we have in one D is the limit as x goes to infinity, two x sin x. All right. So you said you had some, where did you start running?
I tried to do, the, and I kept. So I think I was doing it wrong because I was taking both the derivatives each time. I guess I was just trying to run through it over and over until I got the right answer, and I was just getting confused on it.
The answer to this actually turned out to be 2/3. So here's a natural thing to do. What's happening to the top? What's it doing? Right, this piece is going to infinity, agree? And this isn't really interfering with it, because this is just a plus or minus one. This is a small error when next gets bigger. Same deal, right? Going to infinity. So you have an infinity over infinity, very natural to try, but we're told. Is this what you got in the first step? Something like that?
Yeah, I just.
What's this? No, actually, unfortunately, this is just a huge mess. In fact, the limit doesn't exist actually at all, because there's a couple problems. What's happening to the numerator? It's wiggling back and forth, right? Because this thing right here is between plus or minus 2, agree? So what's going on here is this is wiggling back and forth between 4 and 0. Random, this goes back and forth. Whereas this goes back and forth this is between plus and minus 3. The denominator is, let's see. Right, so the denominator is going between 0 and 6. And actually that indicates a bigger problem. Right, because every so often this denominator becomes 0, right? And so what does that mean? Like, for example, at 0, this is 0, this is near 4, so it's got like a vertical asymptote. This limit doesn't exist at all. Do you remember what that tells you about a L'Hopital rule? This is kind of a technical thing about the L'Hopital rule that you need to be aware of, because it's important to know when to use a rule and when not to. L'Hopital says if you get infinity over infinity, 0 over 0, you do your little trick, you take the derivative top and bottom and evaluate it again, right? If the limit exists, or you can get 0 over 0 again and keep doing this, but when you finally get to something other than 0 over 0, infinity, then that's the answer. If the limit exists or is plus or minus infinity. Neither one of these. hold. This limit is flat, doesn't exist. It wiggles back and forth all over chaos. It doesn't settle on any number. What does that mean? It means L'Hopital's rule does not work. Can't. Okay. So is everybody okay? You see what's going on with this limit? Why it doesn't just wiggles back and forth? The denominator plus 1 0. This 0 3. So it's got all these asymptotes. So okay, if L'Hopital's rule doesn't work, what do we do now? For very, 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 let me ask you this. This is an important engineering thing. You gotta learn to estimate. What's that? What is that? 2/3. Everybody heard of that? I mean, that almost seems like a bit of silliness, doesn't it? That's 2/3. But that's essentially what's going on here. Because when X is super, super big, this is inconsequential, right? So if X is like, 10 to the 100th power, you couldn't even put this in your calculator because there'd be 100 digits between, your top significant digit. This that almost doesn't change anything. So this is almost no different from 2X when X is larger. So my intuition tells me this should be 2/3. Let me put that into mathematical practice. Divide top and bottom by X. Limit as X goes to 10. 2 plus 2 sine 2X X plus sine 2X, correct? And 3 plus cosine 3X over X. Right, see what I did there? It's a little out, right? Because that numerator between 1 and -1. There's the denominator. And as X goes to infinity, 1 over X and -1 over X both go to 0. So where does this have to go? There's something similar going on here. X goes to infinity, these go to 0. So does that. What theorem is it? Squeeze there. Very good. These both go to 0 as X goes to infinity. And I'm left with 2. So L'Hopital's rule is very powerful, but you have to be wary. If you ever reach a step, and I knew that's probably what happened, because if you keep continuing this this mess, then you'll get 0, and then you'll get like another sine and cosine. Well, it still doesn't exist. So everybody okay with that? Okay, so I have a request for which one? Eli, you meant quiz 9, didn't you? Is that right? 1 and 2. Okay, so let's do 1 first. So I need the function here. Admittedly, it takes some practice to draw these things. Make sure you're very careful. Give me an excuse to give you some points, right? Tell me what you know about the problem. tell me what happens to the function as it goes to infinity, if appropriate. Tell me what happens near singularities, if it's got anything to do with the domain is. The more information you can give me, the more I can reward you for knowledge of what's going on. And I also wrote this way. And I gave you the derivatives. Um, for three, 2x plus. Let me take let me sort of feel like one of these FBI guys, right? We're sort of like profiling with serial killers. I want to know all the information about what's up with this thing. By the way, I wrote this way to sort of do you a favor. What happens to this function as x goes to infinity?
You asked about the first one.
No, function itself. Well, actually, let me stop here. What's the domain? One n. You can play any number in you like this, except for 1 and minus. What do you suppose happens 1 and minus? What do you expect to happen? So, yeah, I agree with that. Because notice when x gets very, very close to 1 from either side, this is getting close to 0, this is getting close to either plus or minus 1, this is getting zero. So there's going to be some kind of vertical aspect going on there, plus or minus. Got that. Look at this piece right here. What happens to this piece when x goes to infinity or negative? Just this piece right. What happens to that when x goes to infinity? That it does, because the bottom is the dominant power, right? This is actually going to 0. So I already knew that f of x, so this tells me f of x is approximately equal to x if the absolute value of x is big. So I can already tell you that if you forget about the stuff in the middle, which is where, you graph it on the curve stuff happens, way, way, way out toward infinity, big numbers, way, way out, big numbers, negative. This is going to look almost like the line y equals x. Right, okay with it? Because what this says is this function is the line y equals x plus this little correction. But the correction is getting very, very tiny. Thanks to this law. Everybody understand that? So I already know a bit about this function. It's got slant asymptote. So I know I know it's got 2 vertical asymptotes and a slant asymptote. And so, actually, let me kind of set up the beginning. I'll start. piecing in stuff as I go along. That's one of the. Okay, it's got a vertical asymptote at x equals 1 and minus 1. And it's got y equals x as a slant asymptote. So way the heck off to the right, the function should look like y equal x, very close to it. Well, to the left, it should look like 12. And here in the middle, it quite doesn't look like it's like that's there yet. So let's analyze the first derivative. The critical numbers are what numbers are technically critical? Uh, that answer is technically just a little bit off. Man. They're technically not critical numbers, but we need to plus or minus 1. We need to check them anyway. What's wrong with plus or minus 1? Does anybody remember why technically they're not critical numbers? There's kind of silly things. Well, you can't plug it into the original equation, right? A critical number has to be in the domain, right, which plus or minus this. But when you do a sign chart, you need to consider those. So let's do a sign chart. 0, 1, square root 3, minus 1, minus square root. So prime. All right. Notice that x squared is always positive, and this crap is always positive. Agree? That makes our life very easy just making that observation, because the denominator is always positive, right? And that piece of the numerator is always positive. So the sign is completely controlled by this factor. Right? When this is positive, the whole thing is positive. When this is negative, the whole thing. Right? So where is x squared minus 3 positive and negative? Well, it's negative in between these two. Plugging any number between radical 3 and minus radical 3 is negative, and it's positive outside. So f itself is increasing, decreasing, 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 increasing. What happens here? Good. Local max, and this occurs at minus radical 3, and I guess I can figure this one out. It's gonna be 2 in the bottom, minus 3, radical 3, 2, I guess. And this one right here, the local minimum, isn't it? And it's a radical 3 and 3 radical 3 over 2. That's kind of weird, isn't it? Because the minimum is actually bigger than the maximum. But that's why we're local. What happens here? On local, nothing. But I do know that the derivative is 0. Not critical point, or actually not extreme, but F prime is 0. And these are the asymptotes. I know I've got 0, 0. And then I know I've got a maximum, say here, so I'm gonna flake this out a little bit, but I'm gonna say this is, minus radical 3, whatever it is. Minus 3 radical 3 over 2. My maximum, I'll have my minimum here. Radical 3, 3 radical 3. Well, I've got 3 points. How about the second derivative? What do I need for this? What are my critical numbers? What numbers? What are my important numbers? Second. Yeah, be careful. Almost all of them. 0 certainly. Plus or minus 1 certainly. But this one has no solution, does it? Right, because this is x squared plus 3. Right, so no solution here. So now I've got less, which is good. See what I can figure out about this whole second derivative. These are the asymptotes here. Now notice, in this case, this is always positive. X squared plus 3 is always at least 3, right? So this is positive. We don't have to concern ourselves with this. Let's see what happens. What happens if you're to the left of -1? Something like -10. Well, that's going to be negative, and that's going to be positive. So we bring it up to negative. What happens if you're between -1 and 0, something like -0.5? That's going to be negative, and that's going to be negative and positive. What about 1/2? Positive, negative. And what about beyond 1? Something like 100, positive, positive. This is concave down, concave up, concave down, up. And this is point of deflection. That is concavity action. Changes sign of like point 0, 0 on the function. Notice -1 and 1 are not points of inflection because they're asymptotes. The concavity does change, but it jumps across an asymptote. Hey, with all the stuff we've collected, I think we've got something to go. Let's do this. Let's do this over on the left side first of x equal -1. What happens? Well, on the left side of -1, I'm always sad. I'll always be sad. And it's increasing until I hit that local max, and then it decreases to that asymptote. So it's coming off a y edge like this. Increasing and then it decreasing. Notice it's always unhappy. What happens in the middle, right? Between the vertical asymptotes, -1 and 1, it's always going down. It's got a 0 slope tangent at 0, and the concavity changes. It's happy, sad, always going down, and a 0 slope tangent there. So it's going to be something like this. Now, what happens on the right side of x equals 1, the asymptote? Well, from now on, it's always happy. It decreases off the vertical asymptote and then increases up after it hits local min and tries to get closer and closer to line line. So that's what this is. Any questions? I see how we kind of deconstruct it. So remember, it does take some practice drawing this. So practice a few of these tonight, look at some of the old problems and stuff like that. But on the exam, make sure that you communicate. We are human beings. Communicate me, person to person. Let me know what you know about this problem. Sometimes it's hard to take this information and put it over there. I totally get it. It takes a lot of practice. But tell me that you know where on the exam, you're not going to get the kind of prompts that you did on the quizzes where I say, analyze first derivative, tell me where it's increasing, decreasing, the local extrema. Tell me that when you work out these problems. Okay, any questions on that? Okay, let's look at number 2. And this one, oh yeah, so I did a little roll. Unlike the previous one we had x cubed over x squared minus 1. Now we have x squared over x cubed minus 1. And there's a couple striking bit. Notice in the previous one, I rewrote the problem so you can figure out what the slant asymptote is, right? What happens to this function is x goes or negative? If x goes to negative infinity or positive, this function goes to 0. How can you tell? The bottom is actually bigger than power, right? It's actually bigger than power. If the powers were tied, it would be the ratio of the leading coefficients. But here, the bottom is winning. So this has an asymptote, but it's horizontal. So let me notice the limit is x goes to plus or minus equal to infinity of f of x 0. So it's got the x-axis as an asymptote for both directions. Last example, I had 2 vertical asymptotes. What happens here? Do I have any vertical asymptotes? Only x equals 1. Because if you set that bottom equal 0, you get x cubed equals 1, and the only real solution to that is x is 1. Right, okay? So here, we'll start drawing this one too. Here's x equals 1. It is a vertical asymptote of my function, and this thing is a horizontal asymptote. So I know for very big values of x, positive or negative, this function is nearly 0. And it has some vertical asymptote in the middle. Okay, so the derivatives given to me were f prime of x is equal to negative x, x cubed x cubed plus two. Squared. And two times by the way, this is just kind of for your own interests or whatever. You can actually solve this zero. I'm gonna do that real quick. Does anybody know how you can solve this equation? It's awful intimidating, isn't it? So when you're hunting for these critical numbers, you're looking for the numerator and denominator is zero, right? How would you solve this? I want to do something. Let's do this little thing. Let's take this simple. Notice that 6 is twice 3, isn't it? Right, so the powers are actually powers of 3. So what's u squared? U is x cubed. U squared should be x to the lower power. So this now becomes u squared plus 7u. And you can solve that by your old friend what? -7 plus or minus the square root of 49 minus 4. 49 minus 4, right, over 2. So you get two solutions, the plus or minus. So you get x cubed is -7 plus square root of 45 over 2. And you also get x cubed is -7 minus, right, 45 over 2. And if you take cube root of those, but I shortcutted this for you. It said it's like what, -0.5. So you don't have to be able to solve this because some of the ones that they come out with derivatives are too hard for you all to solve for in closed form, certainly on the test. But anyway, does everybody understand how we did that? So that's a trick. We solve the 6-degree equation. Can't always do that. Okay, so roots x6 plus 7x cubed plus 1 are approximately equal to -0.5 and -1.9. Okay, so I'm gonna kill this. All right. Let's do what we did before. Let's just analyze the derivatives here. And let's see, what numbers do we need to analyze? Consider x equals what? What is it? 0, what was it? 0, 1, I agree. Anything else? That's correct. Or that makes this cube root negative. Right? 0 comes from this, cube root of -2 comes from this. And 1. Only the first and the last are truly critical because 1 is not in the domain. We need to consider all of them. Okay. All right, well, let's see what happens here. All right, let's check this out. Notice first that this bottom is always positive. So this piece doesn't ever affect the sign. All right, what happens then? Sign is determined by the numerator. What happens if x is very, very negative, something like -100? Then that's going to be positive, negative, so this is going to be. What happens if you're between negative cube root of 2 and 0, like -1, for instance? That's going to be positive, positive. What happens if you're between 0, something like 1/2? Well, now that's going to be negative, positive, so it's going to be. And what happens if you're beyond 1, say 1,000,000? Negative, positive, so it's going to be. Yeah. So let's see what we got here. Looks like it's decreasing, then it's increasing, and then it's decreasing. There's your asymptote, and then it's decreasing again. What happens to them? Good. Open it. At -2 to 1/3, and whatever you get with one, I don't really care that much. But I guess it's going to be, so if you cube that, it's going to be -2, -3 squared. It's going to be some negative. Whatever you do, it's going to be both of these. Then it increases. What happens here? At 0, it's a local max. Notice, I didn't notice that this number here, the y coordinate locally is negative. And that's good because then it goes up to 0, better not have been positive. It have to go down to that. And here, nothing occurs here. This is the asymptote. Let's look at the second derivative. Need to consider x equals 1. And these other flaky ones that I gave you. Notice this will make things easier, I guess. So 2 minus 1. So this is actually, this will make our analysis easier. This is actually negative. Between, minus 1.9 and minus 5 and positive outside. These are the two roots. These are the two places where this changes sign or can change sign. And notice between them is -1. If you plug in -1 to this, you get like -5. So that means between these two roots, it's negative, and outside of that, positive. So let's put this all together. What happens if you're to the left of -1.9, say -10, right? Well, that's positive. And that's gonna be negative, it's negative. So it looks like the grand total. What happens if you're between those two roots in this range here, -1.9 and -1.5? Well, this piece is negative between its roots. And this piece, well, so you're negative. So it's negative, so the grand total is positive. Negative from this and a negative contribution from this makes grand. Right, okay. Although, let me go through too fast. Are there any questions? What about between -0.5 and 1? Who obviously needs to check 0. But so you're putting 0 here, you get positive, negative. So it's negative. What happens when you're beyond 1? Something like 10. This is certainly positive. Now that's positive. So it'll be positive. So I get concave down, concave up, down, concave up. And these are points of inflection. That occur at -1.9 and minus, for the x values, -1.955. Get the true points, I'd have to plug this in, but don't bother. I don't need that kind of exactly. Okay, so let's see what this looks like. Let's give this a shot. What happens? I have a local min at minus the cube root of 2, which is more than 1, I guess, and some negative number. So here I have a local min. I don't know. Because I'm too lazy to plug in the coordinates. Okay. Remember, the function goes to 0 as you go to -infinity. And what's happening? It's decreasing always. And it is -2 to the 1/3 somewhere in this range. So I guess it's always concave down until so. Here, so local min, and then it starts up. Now let's see what happens. It goes up 0, 0, which is the local max. So between here and here, it goes up, and then after it goes down. Right? What happens to the concavity? Well, a little bit after this, it changed after where we got at about -1.9. Actually, it's already changed. Okay, not bad. I should flex this a little bit. So the concavity has already changed. It's -2, -1.9 is a little bit further out. Let's see. Brownie, spots. Of course, -1.9 is certainly the left, -2 to 1/3. It's concave up until I get to -0.5 about. And then it goes back to concave down. And it stays concave down, heading down. Yes. So I'm gonna punch this in, smile county. Between these things, it's concave up, concave down outside, so I think I've got just this. Notice how I fudged it, I put in, because it's hard to break the concavity change up in my eyeball. But at least I've got the numbers on right. Everybody see what I've done so far? Okay, what happens after the asymptote? Actually, it's very easy after the asymptote, because it's always decreasing, it's always happy, and it should go to zero as it goes to infinity. So there you go. Always decreasing, always happy. Which is any questions? Is that clear what's going on? Of course, you might also ask, why do we stop at the partial derivative? That's because it's harder. Do you all find it very easy to see where this is increasing and decreasing when you look at this picture? You can tell where it's going up and going down. Do you find it harder to visualize when concavity's changing? I know right here it's frowning. I know right here it's smiling. Somewhere in here, it changed, and it's hard to pick up visually, isn't it? There's the third derivative, right? That's the change in concavity. There's the fourth derivative, change in the change. So this gets harder to pick up visually, and also it gets harder to get so bother with it really. But for lots of functions, and this will be something to learn tonight as well, there's a lot of functions that if you know all the derivatives at a certain point, that information. So for a large class of functions, if I just give you one point, and I tell you, I know what every derivative of this function is at this point. The value of the function is 2, the first derivative is 1, second derivative is 7, the third derivative is -13. That's enough information to tell you the function does everything. Right, for a large class of functions, and that's actually fantastic. But when we graph these things, usually we just mess with first and second derivatives, because for the human visual eyeball thing, that's usually close enough to blocking. Okay. Any questions on that? Okay. Other questions? Number 3 on the quiz. One plus AX to the P of X. First thing, if I look at it, so again, and there's all kinds of weird stuff going on with this. The base is getting close to 0. I'm sorry. The base is getting close to 1, no matter how you cut it, right? I mean, forget about the exponent. 1 plus AX, plug that into 1. Okay. What's happening here? Well, I don't really know, because one thing for sure is that this thing is getting very, very large. Whether it's positive or negative depends on what the sign of B is. It also depends on which side you're coming in from. Right? But what do I have here? I have a 1 to the infinity or 1 to the negative. Oh, unless B is 0. And if B is 0, then this thing is just 1 and the limit is 1. Right? Gosh, there's a lot of things to digest here. But what I have is, for the most part, a 1 to the infinity. Okay? Let's I don't know what you call it. But here we have variable base, variable exponent. Let's do this way. Agree? And one more step. I'm gonna bring, this is the whole point of the introducing the log. Bring it VX family. Do I understand? So let me take one of my patented sides here, figure this out. Simple limit. Uh, let's focus on this exponent, see what's happening to that. What happens if I'm a boneheaded boy? I get log one, which is zero, over zero. So this is prototype below. Derivative of x is one. Derivative what's the top? What's derivative of log of log? I'm not done. I've got to multiply by the derivative of what I'm inside, which is. Okay. Good. So, well, this is just a plug-in job. I'll plug in x zero. So what's the answer to this? E. Notice the observation that I made at the beginning of the problem, that if B is zero, and this thing is just one, and the answer is one. If B is zero, one will give you one. Same thing if A is zero, so that'll be one to some power, it's gonna be one. A or B is zero, it'll give you one. Okay. Any questions? No, I can access it. Oh, this is, were these problems about finding the maximum and minimum values on the indicated intervals? Okay, so this is one of the central problems. In fact, a lot of what we do. So a good chunk of stuff that we'll do later, when we do applied optimization problems, which of course will be central to anybody that's doing engineering and science. I mean, it's all about their economics, you're all about optimization. These kind of problems will be turned to applied problems. These are very important problems. The first one, we want to find the maximum and minimum values. This function, f of x, x4, say x squared. Yep, on the interval minus 1 to 3. find the extreme of that function on that interval. Okay. Please remember this procedure because these are this should be easy points because you just kind of go through this sort of thing. What do you need to do? The first thing you need to do is you send out your dragnet, round up the suspects. How do you round up the suspects? Take a derivative and find the critical numbers. Practice these problems all the way through. I have found with many calculus classes, the mechanics of doing the calculus is not so bad. Make sure that you do your alpha well, be careful with it. I like to factor this. It makes it easier to see what's going on. There's your derivative. What are the critical numbers? Okay, good. The next question is, are all these critical numbers germane to our problem? One of them's not. Right. This one, we can forget about. This is not in the interval minus 1 to 3. So there's only 2 of them that it's like, you've got these 3 suspects, they're hard cases, we know they're up to no good, but this one's got an alibi, he wasn't even in the state, right? So forget about this, we're gonna check out these other 2. Okay, and now rounded up your suspects. Plug them in to the original function. Don't plug them into the derivative, it'll give you 0, you'll be embarrassed. This one gave you 0, but that's a coincidence. This one probably won't. It gives you 16 minus 32, which is minus 16. But there's a couple other suspects that we have not brought down to the station yet. Who else? That's right. You always got to check the endpoints with this. Don't forget that. So f of -1 is 1 minus 8, which is -7. And f of 3 is 81 minus 72, which is 9. So, give me a conclusion too. What are the extremes? Maximum 9, and it occurs at x equals 3, and the minimum is -16, and it occurs at x equals 2. So that's kind of a complete formula. Okay, questions? There was another one. This is a little bit tougher, I think. A sine x plus b cosine x on the interval of 0 to 5. We'll have to make an assumption on the way. I may have actually, there may not be complete information. Saying if I no, I'm gonna go through this carefully. Okay, this is a continuous function on the interval. Right, that's the steps. Round up the suspects. So I gotta take a derivative. What's the derivative of base sin x? But. The derivative of this. Sin x. So I need to find where this is, zero or. Um. Well, let's set this equal to zero, because this function, a cosine x minus b sin x, that's never gonna be nothing. That's always. zero. So if I set this equal to zero, I get a cosine x b sin x. By so I get. Now, let's see how equalized you are. I made an assumption in the last step. Well, I mean, in a certain sense, but just to write this fraction in the first place, what has to be true? There's one thing being. So is not zero, and then we'll come back and see. But actually, the answer would be is. So, we need a critical, right? So how do you find the critical? And if I gave you a fraction, it would be calculated, push the inverse tangent. So, anybody know what the problem is with this stuff? Let's actually do this on the interval problem. Minus power 2, 3 power. Oh, no, we're gonna do this original problem, but I'm gonna change it. This makes me want to change it from 0 to 2 pi to the interval from minus power 2 to 3 power. It doesn't make any difference at all. That's right. Both of those are intervals linked to pi, right? They're 2 pi long. So the maximum end is going to be the same because a sin x equals b cosine x is periodic. Everybody okay with that? Why do I prefer the blue for this problem? Fantastic. The inverse tangent, if you ever return on your, do a calculator. This always returns a value between minus pi over two and pi over two. And if it actually returned a value with zero minus pi over two, it wouldn't be in my range, so, or in my thing, so I just said, well, let's just redo the interval. Okay, so how many critical numbers? It's a little tricky because think of the circle this way. So we're going from minus pi over two to three pi over two. Now this returns some value, some angle x. Whatever it's saying, the inverse tangent a over b. But this one should work as well. Right, the one that's right across it, because it's got the same tangent. So I get two answers. I get two critical numbers, x equal inverse tangent a over b, and I get x equal inverse tangent a over b plus pi. That's right, it just goes 180 degrees, and that angle there will have the same. Okay, so here's what we check suspects. Okay. Check our endpoints. Minus pi over two, this is -1, and that's 0, so I get negative a. I plug in minus pi over two, that I get -1 times a and 0. What happens if I get 3 pi over two? I think I should probably do the same thing. We'll see. Sine of 3 pi over two is also -1. So with two endpoints, what about at now? Let me also this. Now for this one, I'm going to write this. I'm going to use the sign u Sin X, cosine Y, plus cosine X, sin Y, cosine X plus Y, cosine X, cosine Y. Anybody remember that? Maybe you didn't remember, but you know that it exists, right? Remember, this is one of the things you can ask for free. Although, when I put this problem on there, I think I coached them a little bit. Or I can't remember. Right out of it. Okay, so let's see what this does here. This is gonna be sine, cosine, so it's gonna be minus A sine tangent inverse A of B. And cosine pi, take it one. And then it's gonna be cosine sine, sine of pi 0. So that's gone. And this is going to be cosine cosine. Minus sine sine, which is. So basically, this just changes the sign. That's all you can. Agree? Okay. Now, I guess the problem is we have to be thinking. How do you know which one? Well, I'm gonna show you a trick. This will be also very useful if they may. I'm gonna figure out what these things are. How many think this is in track? What is the cosine of this? What's the sine? It seems awful, doesn't it? But it's not so bad. Think of the inverse tangent of something you can angle. Call it theta, just for jollies. This means the tangent of theta is A over B. Correct. So inverse tangent of A over B is an angle called theta. So the tangent of theta is A over B. So let me draw a triangle that meets that description. Tangent of theta is A over B. See how I've got that triangle from this equation? What's the hypotenuse? What's the distance side? What's it? Well, yeah, but I mean, can you think of this in terms of Pythagoras theorem? So notice that the sine of theta, which is the sine of the inverse tangent of A over B, is equal to something is A over the square root of A squared plus B squared. And the cosine of theta, which is the cosine, is actually B over the square root of A squared. Because cosine is adjacent. Does everybody see where I got this? So let's go back and see if we can figure out. This is A times the sine of the inverse tangent of that thing, which is A square root of A squared plus B squared plus B cosine of the inverse tangent. So it's B so this is A squared Because that's a squared over this thing, which b squared, right? So put it over the c. Agree? And this is. This is a squared plus b squared first, a squared plus b squared equals half. So like that. A squared plus b squared. And this is, of course, is minus. Notice these are both bigger. So let's pretend just for a moment the day is big, or the day is positive. This is, day is positive. Then this is minus a, which is minus the square root of a squared, which is bigger than minus the square root of a squared plus b squared. And it's certainly less than this as well. So the maximum and the minimum is that. Anybody remember early on what our assumption was? B is from 0. What happens to B at 0? Then my function g of x is just a sine x. Because there's no b. Alright. And notice sine x is always between 1 and minus 1. So this is always between plus a and minus a, which is the same answer here. Because if b is 0, you get the square root. That's the absolute value of a and minus the absolute value of a. So even though I couldn't divide by 0 there, it gave me the same answer. It all came out in the wash. Everybody understand? That is a hard find the max and find the min, right? If you've got the numbers down, like the ones like the previous one, then you should be pretty good to go. Okay, other questions? Sure thing. Consider the function f of x is x to the 1 over, this is a. Y'all have calculated anything? Or not on your phone? Don't ever tell you, don't ever tell me I never gave you anything. I'll tell you how to win a bar bet. So pick any number you want to place in this function. Well, of course, it has to be constant. And not 1. Any number. Pick a number. Put that in. Pick a number. Right, give it the number, but then find that out. No matter what number you put in, here's the first decimal. Am I correct? I don't care what number. That's. No. Yeah, you can win some bets for that one. And so, No, I did not have a stroke, that there is meaning to this problem here. We look at the function f of x, which is, x, one over natural x. Looks pretty complicated. On the interval one infinity, and of course that means I don't include one, because that would be one over zero in this number. Find the derivative of f of x, and what does your answer tell you about the nature of f of x on the interval? Okay, first thing you gotta do is this. Find y prime. That's essentially what you're doing in this. Okay, so how do we go about dealing with this kind of function?
Take the question.
Right, because your problem is you've got variable base and variable exponent, right? You need to somehow take care of that problem. So let's take the natural log of both sides. And what does this allow me to do to that exponent? This is the whole point. I can bring it down. Right? And what does that turn out? One. Now, let me do something naive and then I'll do something practical. Here's the equation that we have. Natural log y is equal to 1. What do we do now? You could do that. Sure. What's the derivative of log? 1 over y prime. What's the derivative of this side? Multiply both sides by y, I mean y prime is 0. What do we know about a function whose derivative is 0? This is one of those things we did with Rolle's theorem. The derivative is 0, the function must be that's right. Okay, the function has to be constant. The derivative of this 0 is the function constant. Here's another step. Here's another sort of route that we can take. Just look at this freaking equation. Now take the exponential of both sides. So I get y equals e. And there you go. Your function that you started with is actually always e. And that's how I knew what the number was. 2.7182818. That would be the first few decimals. So in answer to the first one, we got that the derivative was 0, and by Rolle's theorem, mean value theorem, whatever you like, a consequence of that is this function is always 0 on that interval, so it's constant on that interval. It then says find the exact value of f of pi squared over radical 5. Somebody tell me what this is. That's right. It doesn't matter what I put in there, as long as it's bigger than 1, it's always e, the constant function. And then part C says f of x is not defined at x equals 1. What value can we assign to f of 1 to make f of x continuous on the domain from 0 to infinity? What you want there is Yeah. Just again. Yeah, he is the answer to part B and C there.
Last question.
And something like that. So I should, does that help out? Okay. What else we got? Hmm. Okay. If you want more practice problems, you can look on my own calc. So they would be called on my webpage, either Math 160, so it sounds like 20%, or Math 160. If you look, especially at exam 3, probably, look at exams 2 and 3. You guys are closer to 3 now. But you can find curve sketching problems where I do things like this, even derivatives. I talked to somebody about this. How many of you are familiar with Desmos on the internet? Yeah, that is like an infinite answer book, right? So, makes it crazy crap up. In fact, you can do this. You can make up anything you want, and you can calculate its derivatives, so you don't have a problem doing all that. Although I would still, you got to stay in good shape doing the simple derivatives. But I mean, if you got something like the inverse tangent of x cubed over x squared plus 1, you probably want to put it in some kind of thing, and it'll spit out the derivatives. Take those derivatives, find what their roots are, because you can ask the machine to do that, and then take a piece of paper, see if you can take that evidence to figure out what the thing looks like, and then check it versus decimal. So that's a really good exercise.
What's the Desmos? DS.
I think that's right, DSMOS. And if you Google like, online graphing tool or whatever, it'll be the first thing. Did any, how, it didn't appear to have ads on it. Do you know how it makes its money?
With the no ads on the side.
I did, I'm not practicing that, but I don't think that's something.
Maybe it was like a college student who did it for like a final project or something.
Well, it seems to work well.
Or to connect with Chang. Subscription.
Oh, believe me, I paid for the background. So I'm pretty sure you don't pay for it. So. Okay, other questions? Well, this folks, good luck. Practice some problems. Get plenty of sleep tonight. I'll see you all at 8 o'clock tomorrow.